Welcome back. In the last two lectures we discussed transmission of air. Once you transmit the required amount of air to the conditioned space, you have to distribute it properly within the conditioned space so that ultimately comfort conditions can be maintained inside the air conditioned building. In this lecture I shall discuss space air distribution. Okay, so the specific objectives of this particular lecture are to introduce air distribution systems and discuss air distribution performance index, describe factors affecting air distribution, describe performance aspects of circular and rectangular free stream jets, describe various distribution devices, describe airflow patterns, describe selection criteria for air supply outlets. At the end of the lecture you should be able to explain the importance of air distribution and air distribution performance index, list factors affecting air distribution, define blow, drop, spread and entrainment, evaluate performance of circular and rectangular free stream jets, list various distribution devices, draw airflow patterns and finally list selection criteria for air supply outlets. So, let me give a brief introduction to space air distribution. As I have already mentioned, once the required amount of supply air is transmitted to the conditioned space, it is important to distribute the air properly inside the conditioned space. Thus, it is important to design or select suitable air distribution system, and the air distribution system selected should create a proper combination of temperature, humidity and air motion in the occupied zone, and it should avoid draft in the occupied zone. What do we mean by draft? Draft is defined as a localized feeling of cooling or warmth. Draft is measured above or below the control room condition of 24.4 degrees centigrade and an air velocity of 0.15 meter per second at the center of the room. The effective draft temperature EDT for comfort is given by this equation. EDT is equal to dBT minus 24.4 minus 0.1276 multiplied by V minus 0.15. Here dBT is the local dry bulb temperature in degrees centigrade and V is the local velocity in meter per second. So, for comfort requirements, the effective draft temperature or EDT should be within minus 1.7 degrees centigrade to plus 1.1 degree centigrade and air velocity should be less than 0.36 meter per second. So, the air distribution system that we finally select or design must be able to maintain the space occupied zone within these EDT values. Okay, EDT can be negative or positive depending upon the air temperature and the air velocity. Okay. Air distribution performance index or short form ADPI is defined as the percentage of measurements taken at many locations in the occupied zone that meets EDT criteria of minus 1.7 degrees centigrade to plus 1.1 degree centigrade. That means, let us say that in an air conditioned building in the occupied zone you take 100 measurements, okay, at various points, and out of the 100 measurements 80 measurements fall within the EDT range of minus 1.7 degree centigrade to plus 1.1 degree centigrade. That means, the effective draft temperature of 80 locations is within this acceptable range. Then the air distribution performance index of that particular conditioned space is 80, because out of 100 80 points are meeting the requirements. Okay. So, that is how the ADPI is measured. The objective of air distribution system design is to select and place the supply air diffusers in such a way that the ADPI approaches 100%. Obviously, we would like to have a 100% ADPI, that means everywhere the conditions are fall within the acceptable limit of EDT, but this is not really possible. It is observed that the value of ADPI depends very much on the space cooling load per unit area. Okay, so many watt per meter square of floor area, let us say. So, a large value of space cooling load per unit area tends to reduce the value of ADPI. So, this is one of the index using which one can evaluate the quality of the space air distribution. Since the air velocity at the supply outlet is normally much higher than 0.36 meter per second and its temperature is much lower than 24.4 degree centigrade, it has to mix properly with the room air before it reaches the occupied zone. Let me show the typical supply air velocities This table here shows the recommended air velocities for supply air diffusers, and here the criteria is noise. That means if the velocity exceeds this recommended velocities, then there could be noise which is objectionable. For example, for studios and operating theatres, the supply air velocity should be between 3 to 3.5 meters per second, whereas in apartments and office spaces it can be slightly higher, that is from 4 to 5 meter per second, whereas in restaurants and libraries it can be between 5 to 6 meter per second. In supermarkets, where as such there is a lot of background noise, you can afford to go for higher supply velocities, that means you can go up to 6 to 7.5 meter per second. Similarly, in factories and gymnasium you can go up to 7.5 meter per second. So, that is how the supply air velocities are decided or selected depending upon mainly on the noise criteria, okay, which in turn depends upon the application. You can see here that these supply air velocities are much higher than the required velocities in the occupied zone, which lies between 0.15 to 0.36 meter per second. Okay, so the supply velocity is at least one order of magnitude higher than the required velocities in the occupied zone. Okay. So, there should be good mixing so that the temperature and velocity can be brought down to the required levels. So, this depends on the effective design of the air distribution system. The occupied zone here is defined as a space that is within 1.8 meter from the floor and 0.3 meter away from the walls. Okay, so let me just quickly explain this. What do you mean by occupied zone? Let us say that this is your let us say that this is the conditioned space and this is the floor. Okay, so these are all the walls of the conditioned space. So, the occupied zone is where, as the name implies, where the occupants are. So, this is defined as all the space that is within 1.8 meter from the floor, okay, and 1 foot away from all the walls. This distance is 1 foot or 0.3 meters. Okay, so this region is defined as the occupied region, and within this occupied region we have to maintain the temperatures depending upon the comfort requirements. Okay. Now, let us look at design of air distribution systems. The factors that affect the design are velocity of air at the inlet to the supply diffuser, mainly based on the noise criteria, as I have already explained. Then supply to room temperature difference, geometry and position of air supply outlet, position of return air inlet, room geometry, room surface temperature, and finally internal heat sources, for example people, equipment, lighting, etc. So, all these factors affect the design of air distribution systems. The exact prediction of velocity and temperature profiles inside the conditioned space requires simultaneous solution of mass, momentum and energy equations. If you want to find out what is the temperature and velocity at a particular location inside the conditioned space, then you have to solve all these three equations simultaneously, but you find that this task in general is extremely complicated due to the several factors that affect airflow and heat transfer. So, mathematically obtaining the exact velocity and temperature profile is very difficult. However, a basic understanding of room air distribution requires the understanding of the following concepts. One is the buoyancy effect, second one is deflection of air streams, and the third parameter is behavior of free stream jets. So, let us look at these three effects. So, what is buoyancy effect? As you know, buoyancy effect is a result of temperature gradient which leads to density differences. Because of the density differences there will be fluid flow. Okay, so, this is what we know as buoyancy effect, and due to buoyancy effects a supply air stream that is cooler than the room air will drop and supply air that is warmer than the air room air rises. Okay, that means when you are supplying cold air to the room, okay, so because of the buoyancy cold air is heavier than the warm air, so the cold air will tend to drop. Whereas if you are supplying warm air to the room, that means the air that is warmer than the room air, then because of the buoyancy the warm air tends to rise. Okay, so we know this from our basic physics. Okay. However, as far as air distribution for air conditioned buildings are concerned, for thermal comfort point of view, it is important that the supply air stream does not strike at occupancy level. What it means is that the cold supply air stream, let us say that we are talking about air conditioning system for summer, when you are supplying cold air to the room at a temperature of 12 degrees or 13 degrees centigrade, it should not directly drop and hit the occupants. Okay, then the occupants will feel uncomfortable because the temperatures are much lower than the recommended temperatures of 23 or 24 degrees centigrade. Okay, so this is an important factor to be considered. So next factor is as I said is deflection. What do you mean by deflection? When an air stream strikes a solid surface such as a concrete beam or a wall, it deflects. Again, from comfort criteria, it is essential to ensure that due to deflection the supply air does not strike the occupants before it is diffused. Okay, so let me show this. For example, this is where, let us say that the cool jet, we are supplying a cool jet, it is supplied at a height into the room. Let us say that this is our occupied zone, that is 1.8 meter and your 0.3 meters from the wall. Okay. So, due to buoyancy effect, this cold air stream will tend to drop into the room, that means it drops into the occupied zone finally. Okay. And due to the deflection, for example, you can see here that I am supplying cold air from the top. Okay, so as you supply the cold air from the top, because of buoyancy it drops, but on this side you have a concrete beam. So when the air stream comes and strikes this, it deflects. Okay, so instead of spreading like this, it deflects in the downward direction because of the presence of the solid beam here. Okay, so but because of this deflection, it should not so happen that cold air is again directly coming into the occupied zone before mixing with the rest of the room air. Okay, so these are the two factors which have got to be kept in mind while designing supply outlets. Next comes behavior of free stream jet. There are certain terms which we have to understand before we understand the behavior of free stream jets and design of air supply outlets. First one is what is known as blow or throw. This is defined as the distance travelled by the air stream in horizontal direction on leaving the supply air outlet and reaching a velocity of 0.25 meter per second. So this is the horizontal distance, as you can see from the definition, travelled by the air stream. Okay, and at a point where its velocity reaches 0.25 meter per second. The velocity should be measured at a height of 1.8 meter above the floor level, that means just at the upper boundary of your occupied zone. In air conditioning, the desirable length of blow is up to 3/4 of the distance to the opposite wall. This is as far as blow or throw is concerned. Then comes drop. Drop is the vertical distance the air moves after leaving the supply outlet and reaches the end of the blow. Okay, this is the definition of drop. So let me show this schematically. You can see here that again we have cool air jet coming from the top. Because of the buoyancy, it drops down. Okay, so this is coming at some velocity, let us say V naught. Okay, V naught is let us say this is coming at V naught, which is equal to say 3 meter per second. So as it will, we shall see this later, but as this air jet leaves the supply outlet and flows into the room, its velocity decreases, and simultaneously it also drops down because of buoyancy. Okay, so here throw is defined as the distance from this point, that means from this point to a point where the velocity is equal to, or velocity has reduced to 0.25 meter per second. Okay. So when the velocity of the center line reduces to 0.25 meter per second, and which is when measured at a height of 1.8 meter, that distance is called as throw. So this is your throw. Okay. And what is the drop? Drop is nothing but the point at which the air stream has reached a velocity of 0.25 meter per second and the center line of your supply outlet. So this is your drop. Okay. Next, there is a very important concept, that is entrainment ratio. As the high velocity jet called as primary air leaves the supply air outlet, it entrains some amount of room air. This is known as secondary air. Okay. So as I have already explained, you supply air to the conditioned space at a high velocity and low temperature. Okay. This high velocity air, as it flows into the room, it entrains some room air. Okay. That means already the air that is already existing in the room is entrained by this supply air. The supply air is called as primary air, which is of high velocity at the outlet, and this mixes thoroughly with the room air. Okay, the room air is called as secondary air. The primary air plus secondary air is called as total air, and this process is known as entrainment. Okay, that means the entrainment of the room air by the primary air. Entrainment gives rise to motion of room air, and the entrainment ratio at a distance x from the supply outlet is defined as the ratio of volumetric flow rate of air at x to the volumetric flow rate of air at the supply air outlet. That means at x is equal to 0. If I take the coordinate system with x is 0 as the supply air outlet, then entrainment ratio r subscript x is equal to qx divided by qx is equal to 0, where q is the volumetric flow rate of air. Okay, so this is how the entrainment is defined, entrainment ratio. Next important aspect is what is known as spread. Spread is the angle of divergence of the air stream after it leaves the supply air outlet. The spread can be horizontal as well as vertical. Normally vanes are used in outlets, and for diverging vanes, the vanes can be either horizontal, diverging or converging, and for diverging vanes the spread is about 60 degrees, and for straight vanes and converging vanes the spread is around 19 degrees. And converging vanes yield a blow that is about 15% longer than that of straight vanes, whereas for diverging vanes it is about 50% less than that of horizontal vanes. Okay, so let me show this the angle of divergence for a diverging vane. Okay, so again, as I said, this is your supply, this is where your supply air is coming at high velocity, and this is your room. Okay, on this side you have the room, so it leaves the supply air outlet, and as it leaves it spreads. So you can see that air is flowing like this. So this is your spread, and in terms of angle for the vanes are here, these vanes are diverging vanes as is mentioned here. For diverging vanes the spread angle is 60 degrees. Okay, whereas it is 19 degrees for converging or straight vanes. Okay, and this spread can be in this is in vertical direction, and it can be in horizontal direction also, that means perpendicular to the board. Okay. Let us look at circular jets. The principle of the simple circular jet can be used to understand the characteristics of most of the commercial supply air outlets. Okay, that is why we study this, because it is simpler to analyze. Okay, and it also has application. And as I have already mentioned, the velocity decays as the jet enters the room and entrains the room air. And applying mass and momentum balance to the circular jet, the velocity profile for the circular jet is given by this equation. Vxr is the velocity of air at any point defined by the coordinate system x and r, that is equal to 7.41 v naught square multiplied by square root of a naught divided by x multiplied by 1 plus 57.5 into r square by x square whole square. Okay, this is how the velocity profile is defined. So let me show this in a picture, it will be clear. So this is your circular jet. Okay, that means if you look at from this side, it is circular in shape. Okay, so the jet is leaving the outlet. So this is your outlet. So as it leaves, as I have already explained, it spreads. Okay, the air jet spreads, and its velocity varies continuously. Okay, and if I define my x coordinate, so as the supply air outlet x is 0. Okay, and r is like this, the center line r is 0, right. So the coordinate system is like this x is here and r is here. Okay, so at any point, for example, which is defined by r and x, the velocity profile is given by this. Okay, so you can see that the velocity varies in the r direction, and it also varies in the x direction. Okay, and the central line velocity is always obviously highest. Okay, so as r increases for a given x, as r increases the velocity reduces. So this is a typical velocity profile for a circular jet, and as I have already said, this velocity profile is mathematically given by this equation, where Vxr is this velocity profile, and it is a function of x, it is a function of r, it is a function of the supply air velocity V naught, that means velocity at this point, and it is also a function of the area of the outlet. Okay, that means this area. Okay, so from this equation it is very clear that for a given V naught and A naught, V reduces as x increases, as r increases. So obviously as you move away from the outlet, the velocity reduces. Similarly, as you move away from the center line, again the velocity reduces. Okay, and at a given x and r, you can see that the velocity increases as supply air velocity V naught increases and as the area of the supply air outlet A naught increase. Okay, so all these things can be deduced from this equation. This equation is derived analytically and it is available in the book by Schlichting on boundary layer theory. And as I have already explained, from this equation it can be seen that the air velocity in the circular jet decreases as x and r increase and as A naught and V naught decrease. Since the velocity decreases with x and r, the jet spreads as it flows. Okay, so this is you can easily deduce this from this equation, that since the velocity reduces, mass flow rate has got to be conserved. Okay, so mass flow rate is given by rho into A into V. If you are assuming that rho is constant, then A into V should remain constant. So as V is reducing, obviously A has to increase. Okay, this comes from your conservation of mass. Okay, A has to increase means the air jet has to spread. Okay, so you can get this conclusion from the equation given above. Okay. Again, from momentum conservation, it can be deduced that entrainment of room air takes place as the jet moves away from the supply air outlet. Okay, so momentum has got to be conserved. So if its velocity of primary jet is reducing, obviously it has to entrain the secondary air so that the total momentum remains constant. Okay. And from this equation, the velocity of air in the circular jet along the center line, that means when r is 0, is given by this equation Vx at r is equal to 0. All that you have to do is put r is 0 in the equation shown before. So you get this expression 7.41 into V naught into square root of A naught divided by x. Okay. So this equation actually can be used to obtain the blow or throw. Okay, because you know that the velocity has to reach, let us say 0.25 meter per second. Okay. At that is the distance called as blow. So if you put 0.25 meter per second, then for a given V naught and A naught, you can find out what is x. That x is nothing but your blow or throw. Okay. And the entrainment ratio of circular jet is given by this equation, as I have already explained before. Rx is equal to Qx by Qx is equal to 0. That means you have to integrate this Vxr over the entire area. Okay, 2 pi r dr. R varies from 0 to infinity, divided by this is the flow rate at the supply air outlet A naught into V naught. So if you substitute the expression for Vxr and integrate it from 0 to infinity, ultimately you find that the entrainment ratio is given by this equation. That means the entrainment ratio is equal to 0.405x divided by square root of A naught. Again, from this equation you can see that the entrainment ratio increases as x increases and entrainment ratio decreases as A naught increases. Okay. Normally diffusers are used in circular jets. Normally you do not have hollow circular jets. Okay, the diffusers are used in circular jets. What is the purpose of the diffusers? These diffusers provide rapid velocity decay and large entrainment and thereby prevent draft. Okay, so that is the reason why diffusers are used. Next, for rectangular jets, long rectangular grills are commonly used for distributing air in conditioned space. Okay, so both rectangular as well as cylindrical jets are commonly used. So for rectangular jets, the velocity profile is given by this equation Vxy is equal to 2.40 multiplied by V naught multiplied by square root of b divided by square root of x multiplied by 1 minus tan h square multiplied by 7.67 y by x. Okay, and here what is b? B is the width of the opening and y is the normal distance from the central plane. Okay, and central line velocity decreases more rapidly for a circular jet compared to a rectangular jet. If you compare these two equations, you find that for a circular jet the central line velocity decreases much more rapidly compared to a rectangular jet. Okay. Next, let us look at types of air distribution devices. First, most commonly used air distribution device is called as grill or resistor. A grill is an outlet for supply air or an inlet for return air. A grill can be used both as an outlet for supply air or as an inlet for return air. Okay. And what is the difference between grill and resistor? A resistor is a grill with a volume control damper. That means grills do not have any volume controls. control dampers. If you have a volume control damper on a grill, you call it as resistor. And they can have fixed or adjustable vanes for deflecting airflow, and they are either ceiling or sidewall mounted. And grills have a comparatively lower entrainment ratio, greater drop, longer throw and higher air velocities in the occupied zone compared to slot and ceiling diffusers. Okay. So, let me show the schematic of a grill. You must have seen this kind of grills in air conditioned buildings. As you can see that this is where the open areas are where from the supply air comes out. Okay, supply air comes out like this, and it has this grill has vertical vanes and horizontal vanes. Okay, these are the vertical vanes. Okay, and all these are the horizontal vanes. Okay, so behind the grill you have the supply air duct. Okay, from the supply air duct, supply air comes, flows through the openings in the grill and enters into the conditioned space and gets distributed properly. Okay, and you have an outer frame. Right, and as I said, these vanes, the vertical and horizontal vanes, can be fixed or adjustable. If for example, in some of the air conditioners they are adjustable vanes, so you can adjust them so that you can deflect the airflow. So, grills and resistors are quite commonly used. Next commonly used air distribution device is what is known as ceiling diffuser. A ceiling diffuser consists of concentric rings or inner cones made up of vanes arranged in fixed directions. They are round, square or rectangular in shape. That means you can have round ceiling diffuser, square ceiling diffuser or a rectangular ceiling diffuser. And supply air is discharged through the concentric air passages in all directions. Ceiling diffusers can deliver more air compared to grills and slot diffusers. So, this is a characteristic of ceiling diffuser, and they provide large entrainment ratio and shorter throw. Okay, so because of these characteristics, they are suitable for higher supply air temperatures and for conditioned spaces with low head space. Okay, that means if you have a air conditioned building with low ceiling height, then you can use ceiling diffuser because their throw is less, so the air diffuses fast. Okay, so that there is no danger of cold air entering into the occupied zone. Okay, so these are typical characteristics of ceiling diffuser. So let me show a schematic of ceiling diffuser. Yeah, this picture shows schematic of ceiling diffuser. So cold air comes from the, as you can see, this is your cold supply air. Okay, it comes like this, and you have the concentric areas, flow areas through which flow takes place. Okay, and this is a two dimensional this thing, that means it can be either square or rectangular. That means if you see from the bottom, you can have something like okay, it will be something like this. Okay, it will be looking like this. So air will be coming from here, okay, from here. So it is discharged in all directions. Okay, and this is mounted on the ceiling, as you can see here. That's why you call them as ceiling diffuser. And in this picture, fixed vanes are shown, but you can also have adjustable vanes. Okay. Next, very commonly used air distribution device is what is known as a slot diffuser. A slot diffuser consists of a plenum box with a single or multiple slots and air deflecting vanes. And these are mounted, that means the slot diffusers are mounted either on the side walls or on the ceiling. Okay, so you can mount them on the walls or in the ceiling. And linear slot diffusers mounted on the side walls can be as long as 30 meters. Okay. And these slot diffusers are used both for supply air as well as return air. And linear slot diffusers are particularly suitable for large open spaces that require flexibility to suit changing occupant distribution. Okay, so these are a typical application of linear slot diffusers. Let me show a photograph where linear slot diffusers are used. This photograph, these two photographs show, these are the diffusers. Again here, these are the diffusers. Okay, this is slot diffusers. So cold air comes from this point. Okay, similarly here cold air comes from this point. So you can see that this is a very long diffuser. Okay, it can be as long as I said 30 meter. Okay, in length, right? So you can see that it really matches very well with the building, and it looks very nice. That means they have very good aesthetics. Okay, the slot diffusers, and they match very well with the background. And in this picture the airflow patterns in slot diffusers are shown. For example, for single direction supply, the air supply air comes like this and it goes in one direction, okay, whereas you can also have multi direction supply, that means air comes in this direction, in this direction and in this direction also, okay. So depending upon the type of slot diffuser you can have both the varieties. In addition to the above air distribution devices, you can also have floor mounted grills and diffusers, low sidewall diffusers, nozzle diffusers, light troffer diffuser slots, etc. Okay. Of course, the most commonly used ones are the slot diffusers and the ceiling diffusers and grills and resistors. Okay, but there are some special applications where you may have to mount the diffusers on the floor. Okay, then you call them as floor diffusers. Okay, you can also have low sidewall mounted diffusers. Okay, this also depends upon the application. For example, some of them are good for heating, some of them are good for cooling. Okay, so depending upon the specific application, we have to select a suitable outlet device. Okay, there is also a special device called as light troffer diffuser slot. Okay, let me show a schematic of this. This is this schematic shows a light troffer diffuser slot. It consists, this actually is a housing which includes fluorescent lamps. These are the fluorescent tubes, okay, or tube lights, okay, and they are installed in the ceiling. You can see that it is installed in the ceiling, and the same housing consists of return air inlets. That means return air goes like this, okay, back to the air handling unit, and they also have supply air diffusers. Okay, that means the supply air comes like this. Okay, that means the same unit combines the light troffer, that means where the fluorescent tubes are located, and it also consists of supply air diffuser and the return air slots. Okay, this kind of unit is called as light troffer diffuser slot. What are the advantages of light troffer diffuser slot? The first advantage is that since the tube lights or fluorescent tubes are surrounded by somewhat colder air, they can have or they can provide better luminous efficiency. Okay, so if you may keep the lights cool, their luminous efficiency increases. Okay, so this is one advantage of having light troffer diffuser slots. Second advantage is that in one unit you get everything. Okay, the light installation and supply and return air inlets. Okay, and it also provides very good aesthetics. Okay, so these kind of units are also sometimes used. Next, let us look at return air inlets. So far we have been talking about supply air outlets. Now let us look at return air inlets. Similar to supply air outlets, return air inlets can be classified as grills, resistors, diffusers, etc. And in many commercial buildings, the ceiling plenum is used as return air plenum with return slots to draw the return air through the ceiling. Okay, that means in most of the commercial buildings, you do not have any return air duct. Okay, that means the ceiling plenum itself is used as the return air duct. That means the space above the false ceiling, the entire space is used for return air passage. Okay, of course the ceiling plenum may consist of supply air ducts. So whatever space is left, that means except the supply air duct, that is used for return air passage. Okay, in such cases you have to install return air slots in the false ceiling. Okay, so that the return air can leave the conditioned space through these slots and flow through the ceiling plenums. Okay. Now there are certain requirements of return air inlets. These requirements are, they should not lead to short circuiting of supply air. That means the cold air without mixing with the room air should not simply go back to the return air passage. Okay, so short circuiting should be avoided. And undesirable products such as tobacco smoke, odors, etc. should be able to move in their natural direction so that they do not stagnate in the occupied space. This is very important, and this decides actually where you locate return air inlets. For example, to eliminate tobacco smoke, the return air inlet should be placed high in the wall, so that the tobacco smoke rises because of buoyancy, and if you keep the return air inlet at the top, it naturally flows in that direction and leaves the conditioned space. Okay. So for tobacco smoke elimination, you have to put the return air inlets high in the wall, whereas to remove dust particles, etc., which tend to settle down on the floor, you must keep the return air inlets near the floor. Okay, so that the particles do not float in air. Okay, these are some of the typical characteristics and which must be kept in mind while designing return air inlets. Now let us look at airflow patterns inside conditioned space. In most of the conditioned buildings, air is supplied at a temperature of 10 to 15 degrees centigrade, 15.6 degrees centigrade, and with a velocity in the range of about 2 to 4 meter per second. Okay, these are general values. It can be slightly lower or higher. Okay, these are I am just giving general values. This air, as you can see that the supply air temperature is much lower than the required comfort temperature and the velocity is much higher. So this air has to mix thoroughly with the room air, so that when it reaches the occupied zone, its temperature should be around 22 to 23 degrees centigrade and its velocity is less than 0.36 meter per second to avoid draft. This is very important. The airflow pattern is influenced mainly by the type and location of supply air outlets. The high side outlets, ceiling diffusers and slot diffusers are most commonly used in air conditioned building. I have described these outlets, and in general compared to supply air outlets, the effect of return air inlets is not so significant on air distribution inside the conditioned space. Okay, the supply air outlet is very important, right? And the mixing airflow patterns should have the following characteristics: entrainment of room air, as I have already told you, to bring the air temperature and velocity in the occupied zone to acceptable levels, reverse air stream in the occupied zone for an even velocity and temperature distribution, and minimization of stagnant areas in the occupied space. There should not be any stagnant areas in the occupied space. What do we mean by a stagnant area? A stagnant area is a zone in which the natural convective currents prevail and the velocity is less than about 0.1 meter per second. Okay, so the airflow pattern should take care of all these factors. I am sorry, air distribution devices. Okay, now let us look at high side outlets. High side outlets installed on a high side wall for cooling and heating applications. What is the airflow pattern of these? First, let me describe the airflow pattern. As the air is discharged from the high side outlet, due to surface effect, also known as Konda effect, the air jet tends to stick to the ceiling. The cold supply air entrains the room air and deflects downwards when it strikes the opposite wall. These outlets may lead to draft if the throw is too large or too small. The most suitable location for return air when you are using high side supply air outlets is on the ceiling outside the air jet. Okay, so let me show a schematic of airflow patterns using high side outlets. So you can see here that this is where you have the supply air duct and supply air is coming like this. Okay, so you have the primary air envelope, this dark area is your primary air envelope, right. So it is this jet leaves the supply air outlet at high velocity, and because of the high velocity and as it flows, as it leaves this thing, it entrains the room air. So you can see that room air is entrained. So here you have total air, which is a mixture of primary air plus room air. Okay, and if this is designed properly, what happens is this air, total air and primary air, go right up to the opposite wall. You have the opposite wall here and strike the opposite wall, get deflected like this. Okay, and the reverse air stream flows in this direction. Okay, that means air comes like this, gets deflected and flows like this. Okay, so as it flows like this, it entrains the room air and there is thorough mixing in the conditioned space and there are no stagnant zones when you are using it for cooling. Okay, that means this particular picture is for cooling and when you are looking from the side. Okay, the same thing when you are looking from the end, that means this end view is something like this. This is where your supply outlet is there. Okay, so this is your total air, right, and the reverse air stream is in this area. Okay, and this is the cooling plan view. Okay, so you can see that these are the primary air jets. This is the total air. Okay, and this is where you have reverse air streams. Okay. So as far as cooling is concerned, these outlets are quite good because you can see that there is hardly any stagnant zone. Whereas if you are using these jets for heating, you find that there is a possibility of a stagnant zone. Okay, because when you are using it for heating and when you are supplying warm air, because of buoyancy effect, it tends to stick to the ceiling, okay, rather than coming down. Okay, so as a result, near the floor you may have a stagnant zone. Okay, and you can see here that the air stream, for example, in this picture and in this picture, as it leaves the outlet, it tends to stick to the ceiling. Okay, it is sticking, trying to stick to the ceiling. This effect is known as surface effect or Konda effect. Okay, so this is the airflow pattern for high side outlets. Now let us look at airflow pattern using ceiling diffusers. These diffusers produce a shorter throw, a lower and more even distribution of air velocity, and a more even temperature when used for cooling. However, when used for heating, it is seen that a larger stagnant area is formed due to buoyancy. Ceiling diffusers are widely used for conditioned spaces with limited ceiling height, as I have already explained, and are designed to have a large entrainment ratio and are widely used in variable air volume systems. Okay, so let me again show the airflow pattern. When used for cooling, this is the side view. Okay, so this is where you have the primary air and this is the diffuser. So it first sticks to the ceiling because of the Konda effect, then entrainment takes place and you have the total air here, then the reverse stream starts like this, and there is again hardly any stagnant area in this when you are using it for cooling. Similarly, this is the end view and this is the plan view. Okay, that means you have in this particular view you have only one ceiling diffuser and the air is distributed in all directions. Okay, however, you find that if you are using this for heating applications, there is a possibility of developing a stagnant zone. Okay, again because of buoyancy effect, the warm air tends to rise up rather than come down. So near the floor you may have a stagnant zone. Again, you can also have airflow patterns obtained using slot diffusers. The slot diffusers installed in the perimeter zone discharge air vertically downwards and also in the horizontal direction. Due to its better surface effect, the air jet remains in contact with the ceiling for a longer period, and the reverse air stream ensures uniformity of temperature and velocity in the occupied zone. Due to their superior characteristics and better aesthetics, slot diffusers are widely used in large office spaces with normal ceiling heights and with variable air volume systems or VAV systems. So again, this picture shows the airflow pattern for cooling using slot diffusers. So here this zone is the perimeter zone, that means near the wall, and this is your interior zone. Okay, that means away from the wall. So you have supply slot. This is one. This is one. This is one. Okay. So the supply slot near the perimeter, it air flows in the horizontal direction, air also flows in the vertical direction. Okay. Again, you can see that the reverse air stream is taking place like this, whereas the air that is supplied at the interior zone, it flows in the horizontal direction. Okay. Again, the reverse air stream takes place, and you again find that there is hardly any stagnant zone. So again, these are very good for cooling applications. Next, let us look at selection of supply air outlets. Selection depends upon the following criteria: requirement of indoor environment control. If the indoor environment requires controlled air movement, then a high side outlet should not be used. Okay. Controlled air movement means you want air movement only in certain locations, not everywhere. Then you cannot use high side outlet because you do not get very good control here. And it also depends upon the shape, size and ceiling height of the building. Ceiling and slot diffusers are ideal for buildings with limited ceiling height. For large buildings with large ceiling heights, high side wall mounted outlets are recommended. Okay. Then comes volume flow rate per unit floor area. Side wall outlets are limited to low specific volume flow rates, and compared to slot diffusers, the ceiling diffusers can handle efficiently a larger volumetric flow rates. And this table here shows the specific volume flow rates of different outlet devices. Okay, so here you have the type of outlet: grills, slot diffusers, perforated panels and ceiling diffusers. Here the volumetric flow rate per meter square of floor area. Okay, so this is liter per second per meter square of floor area. So you can see that for grills it is 3 to 6 liter per second per meter square, whereas for slot diffusers it is higher. Perforated panel at 4.5 to 15, and for ceiling diffusers you can see that compared to the other types you can have a much higher volumetric flow rates per unit floor area. Okay, again the same thing is given here in terms of maximum air change per hour for a 3 meter high ceiling. Okay, so again you can see that ceiling diffuser can handle large volumetric flow rates. Next important criteria is the volume flow rate per outlet or per unit length. This depends upon the throw required to provide a satisfactory room air distribution. Okay, and this value normally lies between 23 to 62 liter per second per meter for linear slot diffusers, So, if you know the total volumetric flow rate, you can find out or you can calculate what is the length of the slot diffuser required, because you know the volumetric flow rate per unit length. Okay. And for sealing diffuser, for example, a thumb rule says that in a closed office with a floor area of 14 meters square and only one external wall, one sealing diffuser is normally sufficient. Okay. So, again depending upon the floor area, you can decide the number of sealing diffusers. Next comes throw. We have already explained what is the throw. High sidewall outlets have a longer throw than sealing diffusers. Square sealing diffusers and circular sealing diffusers have similar and shorter throw. Okay, so these are the characteristics of different devices. So depending upon your throw requirement, you have to choose accordingly. Then noise level. Okay, so obviously this is very important. Then comes total pressure drop. Total pressure drop generally varies from 5 to 50 Pascal depending upon the type of the outlet and depending upon its design and the flow rate, and normally it should be less than 50 Pascal. Then comes cost and appearance. So these are also important. In some applications cost is more important, in some applications appearance is more important. So depending upon the specific requirement, again you have to select the required type of outlet. Normally performance of various types of supply air outlets are provided by the manufacturers in the form of tables and charts, using which one can select a suitable supply air outlet. Okay. So the manufacturers, after thorough testing, they give their or they publish or print their catalogs, where you can they normally specify the characteristics of supply air outlets in terms of the flow rates, throw, okay, pressure drop, etc. So and noise criteria, etc. So depending upon the requirement and using these catalogs, one can select the required type of outlet, and depending upon the area or depending upon the flow rate requirement, one can decide the number of outlets. Okay. So this is how the room air distribution system has got to be designed, and as I said, this is the last stage of an air conditioning system. Okay, because once you transmit the air to the conditioned space, the only thing that is left is to distribute it properly. Okay, if everything is right but distribution is not proper, then ultimately the purpose is lost, because inside the conditioned space, because of improper distribution, required conditions cannot be maintained, even though the flow rate, everything is all right. Okay, so the air distribution system design is very important. Okay. So with this we come to the end of this course on refrigeration and air conditioning. Okay. So I would like to briefly review whatever we have learned or whatever we have discussed in this course. So we began this course with a short history of refrigeration. Then we have discussed the applications of refrigeration and air conditioning. Then we briefly discussed the fundamentals of thermodynamics, fundamentals of fluid flow, and fundamentals of heat transfer. Okay. After that, we discussed what are the various methods by which low temperatures can be obtained. Okay. Then we started our course proper with air cycle refrigerant systems. Okay. So the different cycles, ideal cycles, and analysis of air cycle refrigerant systems have been discussed in that lecture. Okay. We have also discussed briefly the cycles for aircraft air conditioning. Okay. Next we started discussion on vapor compression refrigerant systems, and this we have studied in great detail, because this is one of the most widely used among all the refrigerant systems. So we discussed starting with the ideal vapor compression refrigerant system, actual vapor compression refrigerant system, analysis of the cycles, okay, and the difference between actual and ideal cycles. Then we have also discussed various multi-stage, multi-evaporator and cascade cycles and their performance characteristics, and the performance analysis of these systems. Okay. Next we discussed again in somewhat detailed manner vapor absorption refrigerant systems. In vapor absorption refrigerant systems, we began the discussion with water lithium bromide systems, in which water is used as the refrigerant and lithium bromide is used as the absorbent, and as I have already told you, if you remember, this is mainly used for air conditioning applications. Okay. Next we discussed vapor absorption refrigerant systems based on ammonia water, which can be used for both refrigeration as well as air conditioning applications. Finally, we also discussed triple fluid or pumpless vapor absorption systems briefly. Okay. So next we discussed the system refrigerant system components. So, compressor is one of the most important component of vapor compression refrigeration system. So, we studied this component in great detail, and during this we have studied the performance characteristics of reciprocating compressor, centrifugal compressor, and other positive displacement type of compressors. Okay. Next, we also discussed the performance characteristics, design aspects of condensers and evaporators. We have seen different types of condensers and evaporators and how to design them, okay, from the given input. Then we discussed expansion devices, starting with capillary tubes, thermostatic expansion valves, automatic expansion valves, and their performance characteristics. Okay. Then finally we have discuss the analysis of a complete vapor compression refrigerant cycle. How do we balance the components? Okay, as you know, in a typical vapor compression refrigerant cycle, 4 basic components are there. So, how a balancing between the 4 basic components take place? This was discussed briefly. Okay. Next, we also discussed the very important topic of refrigerants. Okay, what are the selection criteria and what is the importance of refrigerants in view of the ozone layer depletion and global warming potential, what were the older refrigerants which were replaced because of these environmental problems, and what are the new refrigerants which are eco-friendly. Okay. So, these aspects were discussed in refrigeration in the lecture on refrigerants. Okay. Next, we started a discussion on air conditioning with psychrometry. Okay. So, we defined basic psychrometric properties, then we have looked at psychrometric chart, okay, and various isolines on psychrometric chart. Then we have drawn or we have analyzed various psychrometric processes using the psychrometric chart. Okay. So, this is the fundamental to the analysis of air conditioning systems. Okay. After the psychrometric this thing, we have psychrometric processes and psychrometric charts, psychrometric properties, etc. We looked at air conditioning systems, okay, different types of air conditioning systems and the psychrometry of these air conditioning systems. Next, we studied how to select the required design inside, outside and supply conditions. So, for selecting the inside conditions, we have to take into account the comfort criteria as far as the comfort air conditioning is concerned. So, I discussed the thermal comfort criteria, what are the different factors that affect thermal comfort, right, and based on that how do you fix the required temperature, velocity and relative humidity inside the conditioned space, which have got to be maintained by the air conditioning system. Okay. Next, we have also seen how to select a proper outdoor design air condition based on the weather data. Okay. Next, we began a very important discussion on the design of on the cooling and heating load estimations. Okay. This is very important to arrive at the required cooling capacity or heating capacity. So, in this particular lecture, which we have studied in somewhat detailed manner, we have seen how to take into account the solar radiation, how to take into account opaque walls, transparent walls, right, and the radiation loads, etc., and how to estimate finally the required building cooling load and the system load using the heating and cooling load calculations. Okay. Then we have seen air conditioning systems, different types of air conditioning system and their characteristics like all air systems, all water systems, unitary systems, air water systems, etc. Okay, performance characteristics and the layouts of these systems, right. Then we have discussed transmission of air, basically what are the basic laws that govern the transmission of air through ducts and how to design ducts, and we have looked at 3 basic duct design methods, that is static regain, a velocity method and equal friction method, and we have also seen fan laws and how to use the fan laws. Finally, we have discussed space air distribution briefly. Okay, what are the different factors that affect the space air distribution, how to select or design the supply air outlets, return air inlets, etc. Okay, so with this I complete this course. Okay, there are certain topics which I have not covered are refrigerant and air conditioning system controls and refrigeration and air conditioning systems for mobile applications, for example transport refrigeration or mobile air conditioning systems, etc. Okay. So, these aspects I could not cover because of time constraints. So, you can refer to advanced books or standard books on refrigeration and air conditioning for details on these aspects. Okay. I would like to mention here that refrigeration and air conditioning are very important especially in present days world, where they have become in fact essential items, refrigerators and air conditioners, and since they consume a lot of energy and they have an impact on the environment, one has to understand at least the engineers should understand the various factors, and we should be able to design or select a suitable refrigeration and air conditioning system, so that they serve the purpose with the minimum energy cost and with minimum damage to the environment. Okay. With this I take leave. Thank you very much. Before taking leave, I would like to give some reference books which can be referred to for basic understanding or for further reading. Thank you. Okay.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. At every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning. With the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his